Hello everyone, I'm Shui Chaoshen. Today I'll continue with the 10th grade must-know series, specifically comparing the magnitudes of logarithms. When comparing logarithms, we might encounter cases where the bases are the same, the arguments are the same, or both are different. If the bases are the same, we can directly use the monotonicity of logarithmic functions. As long as the base is greater than 1, the logarithm with the larger argument will be larger. If the base is between 0 and 1, then the smaller the argument, the larger the logarithm. Now, if the arguments are the same, we just need to take the reciprocal, because when the base and the argument are swapped, we get the reciprocal using the change of base formula. This means log base a of b equals 1 over log base b of a. Okay, now let's look at this. Here, a equals log base 3 of 1/2, b equals log base 1/4 of 10, and c equals log base 2 of 1/3. If both the base and argument are different, we need to find an intermediate value like 0, 1, or -1 to compare them. Now, looking at this structure, let's see if we can create a common base. We see a 1/4 and a 2, and there is a clear relationship between 1/4 and 2. So this means that we can actually rewrite 1/4 as 2 to the power of -2. When moving the -2 to the front, remember that the exponent of the base goes in the denominator and the exponent of the argument goes in the numerator. Then we have log base 2 of 10, so we can move the -1/2 to the exponent of 10. It becomes log base 2 of 10 to the power of -1/2, which is 1 over 10 to the power of 1/2, or 1 over the square root of 10. So for b and c, it's now quite easy to determine their relationship. We know the square root of 10 is roughly 3 point something, which is definitely greater than 3. Therefore, 1 over the square root of 10 must be less than 1/3. Since both b and c are logarithms with base 2, and log base 2 of x is monotonically increasing, the larger the argument, the larger the value. So the logarithm with the larger argument is in fact the one that is larger in value. This observation tells us that b is less than c, because the logarithm increases as its argument increases. Next, let's take a closer look at this relationship and see what else we can learn from it. A, when we process it, you'll see that since b is less than c, we should check their relationship to 0. When comparing them with 0, you'll find that log base 2 of 1 is, in fact, exactly 0. Since c is log base 2 of 1/3, it is obviously smaller than log base 2 of 1. Therefore, next, it's going to be less than 0. Now, using the same formula and the same approach, our value for a here is equal to log base 3 of 1/2, which is definitely smaller than log base 3 of 1, which is 0. Since they're both less than 0, what should I look for next? Well, how about we just use -1? So that means we'll look for -1 next. And for our a, to find -1 using base 3, right? Then -1 would be log base 3 of 1/3, which happens to be exactly equal to -1. Now, for our log base 3 of 1/2, since 1/2 is greater than 1/3, it means that our a is, well, it's greater than -1 and less than 0. It's roughly -0 point something. Okay, so now we need to check if b is less than c. And what we're really hoping for is that b is less than c. And also, what else? Less than -1. So that means we'll take a look next. Your c is log base 2 of 1/3. So when you compare it to -1, you're looking for log base 2 of 1/3 versus what? Log base 2 of 1/2, which is just -1, right? And this thing right here is my c. 1/3 is definitely smaller than 1/2, so log base 2 of 1/3 is certainly less than log base 2 of 1/2, which means c is less than -1, and since b is smaller than c, b is less than c. And then it's less than a, so b is less than c is less than a, which means we're choosing option b. So this means that in this process, if the bases and arguments are different, we often look for values like 0, plus or minus 1, and occasionally plus or minus 1/2, and so on, using these intermediate values and the transitivity of inequalities to help us solve the problem. Okay, now let's try a quick practice problem. We have three numbers, a equals log base 3 of 6, b equals 7 to the power of 0.4, and c equals log base 0.25 of 0.125. Now we can actually calculate the value of c, because when we look at c, the base can be written as 0.5 squared, and the argument can be written as 0.5 cubed. Moving the exponents to the front, the exponent of the argument goes in the numerator and the base's exponent in the denominator, giving us 3/2. Log base 0.5 of 0.5 is just 1, so C is exactly 3/2. So now let's look at number A. First of all, it's definitely greater than log base 3 of 1. It must be, since they're all different now, which means we have to look for an intermediate value. So in this case, A is equal to log base 3 of 6, which is definitely greater than log base 3 of 1. And not only is it greater than log base 3 of 1, it's also greater than log base 3 of what? It's greater than log base 3 of 3, right? Okay, and then next we need to find out how it compares to 3/2, right? Now we know that for 3/2, if I want to write it in a logarithmic form, it would be equal to 3/2 times log base 3 of 3. Move 3 over 2 directly to its exponent, so that means it equals log base 3 of 3 to the power of 3 over 2. Now 3 to the power of 3 over 2, when we write it out, is just the square root of 3 cubed, which is the square root of 27. As for our log base 3 of 6, 6 is the square root of 36, which is definitely greater than your log base 3 of the square root of 27. So this means that A is not only greater than 1, but it's also greater than what? Greater than 3 over 2. Okay, and at the same time, log base 3 of 6 is definitely less than log base 3 of 9. So we can conclude that A is definitely greater than 3 over 2. And less than log base 3 of 9, which is 2. So in this case, the value of A must be greater than the value of C. Now we've found that A falls between 3 over 2 and 2. What we're hoping for is that B is either smaller than 3 over 2 or larger than, well, 2. Comparing it to 3 over 2 is a bit more complicated. So we can try looking at this 7 to the power of 0.4. Comparing it with 2 here seems much easier. If it's greater than 2, then we're all set, right? That would mean B is the largest. Okay, so we can write 7 to the power of 0.4 as 7 to the power of 4/10, which is 2/5. Then compare it with 2. A direct comparison is, well, hard to do. Since we have a fractional exponent, we can use the method of exponentiation. We're basically using the power property of inequalities. Raise both sides to the 5th power. 7 to the 2/5 raised to the 5th is 7 squared, 49. 2 to the 5th is 32. Since 49 is greater than 32, this term is greater, meaning 7 to the 0.4 is greater than 2. So B is greater than 2, while A is less than 2. Therefore, B is greater than A, which is greater than C. Thus, the one we choose is option A. So B is greater than A, which is greater than C. Okay, let's move on to the next one. Now we're told that A is equal to log base 0.3 of 5, and B is equal to log G base 2 of 5. Now, looking at this structure, as you can see, please observe that the arguments are actually the same. This means we can examine their reciprocals. So that means we can immediately see that 1 over A is equal to log base 5 of 0.3. And 1 over B is equal to log base 5 of 2. Okay, so for options A, B, and C, we can actually express them in terms of 1 over A and 1 over B. First, we must pay close attention to this point. We know that log base 5 of 0.3 is definitely less than log base 5 of 1, so it's less than 0. While log base 5 of 2 is definitely greater than log base 5 of 1, so it's greater than 0. So between A and B, A is negative and B is positive, 2. Okay, so that means for option A, its equivalent proof is for us to verify if 2A plus B minus A times B is less than 0. This is equivalent to generating 1 over A and 1 over B. Dividing both sides by AB, the first term becomes 2 over B plus 1 over a minus 1, and the less than sign must change to greater than 0. Because A times B is negative, so that means we'll just verify 2 times 1 over B, which is 2 over B plus 1 over a minus 1. Let's substitute the values in. 2 times 1 over B is 2 times log base 5 of 2 plus 1 over A, which is log base 5 of 0.3, then minus 1. So in this case, 2 squared is 4. So the final result is log base 5 of 0.3 times 4. Because when adding logarithms with the same base, the base stays the same and the arguments are multiplied. So that means we get 1.2, then minus 1. And 1 is exactly log base 5 of 5. So obviously, what is it? It's less than 0. But your equivalent was greater than 0, so option A is incorrect. Okay, next let's look at option B. For the equivalent proof of option B, divide both sides by AB, then B divided by AB is 1 over A minus 2, A divided by AB is 2 over B, then minus 1. Similarly, less than becomes greater than. Next, let's calculate 1 over a minus 2 over B minus 1. 1 over A is equal to log base 5 of 0.3 minus 2 over B, which is 2 times 1 over B, so that's log base 5 of 2, then minus 1. So that gives us log base 5 of 0.3 divided by 2 squared, which is 0.3 over 4. Then 0.3 over 4 minus 1 in log base 5 is definitely less than 0. Since you need greater than 0, it's definitely wrong. Now for option C, when performing the equivalent proof, we divide both sides by a b. The first term is 1 over b. The second is 3 over a, then plus 1. The greater than sign must become less than. So we have 1 over b plus 3 over a, and then plus 1. 1 over b is the logarithm with base 5 of 2. Then plus 3 times 1 over a. 1 over a is the logarithm with base 5 of 0.3. Then plus 1. 1 can be written by us as log base 5 of 5. So that means it's log base 5 of, the first argument is 2, and the second argument is 0.3 cubed. The third antilogarithm is 5, so that means we now need to determine if it's less than 0. To see if it's less than 0, just check if the antilogarithm is less than 1. Multiplying 2 and 5, let's calculate the antilogarithm. 2 times 5 is 10, then multiply by 0.3 cubed. 0.3 cubed is 0.027, so the final result is 0.027. Multiplying by 10 gives 0.27. 0.27 is definitely less than 1, so it's less than log base 5 of 1. It's less than 0, no problem. Option C is correct, so we'll choose option C. Let's look at an equivalent transformation for option D, which is to group them together. Move A to the right side of this position, so that means we get 2A minus A is just A, then move B to the left side. It should be minus. Don't move them the wrong way. Moving to the left, it should be negative 3B is greater than A. Just like before, divide both sides by a b, greater than becomes less than, so that's negative 3 times 1 over a, is less than our 1 over b. So it's equivalent to 1 over b plus 3 over a. On the right side, is it greater than 0? Let's calculate 1 over b plus 3 over a. 1 over b is log base 5 of 2, and 3 over a is 3 times log base 5 of 0.3. So that gives us log base 5 of 2 times 0.3 cubed, which is 2 times 0.027, which is definitely 0.054. So this is definitely smaller than log base 5 of 1, meaning it's less than 0, but you need to prove it's greater than 0. So it's wrong. That means throughout this entire process, you must see if we're studying the same base or the same antilogarithm, or if the base and antilogarithm are different, the strategies used are not quite the same. You must know how to handle it. Because comparing the magnitudes of logarithms and powers like this is very likely to be tested in the exam.